Right now, at this very moment, a rock the size of a 10-story building is screaming toward Earth at 67,000 kilometers per hour. Look at this image. Do you see it? Neither did anyone else. February 15th, 2013, 9 in the morning, Chelyabinsk, Russia. It's a normal Friday. People are driving to work. Then suddenly, something bright is seen in the sky, brighter than the sun. Some even feel the air get hotter. Above them, that building-sized rock, 17 meters across, weighing 11,000 tons, slams into our atmosphere at 67,000 kilometers per hour. 23 kilometers up, it explodes. The flash is blinding. People come to their windows to see what happened. But 90 seconds later, the shock wave hits. The explosion releases energy equivalent to 440,000 tons of TNT, 30 times more powerful than the Hiroshima atomic bomb. Within 4 days, debris from that blast circles our entire planet. And the scariest part? No one saw it coming. Scientists had no idea this asteroid even existed until it was already burning through Earth's atmosphere. What if that rock had been bigger? What if, instead of 17 meters, it were 170 meters? What if it hit a city directly instead of exploding high in the atmosphere? Now imagine it's 2032. A rock the size of a mountain somewhere far off in our solar system is on a direct collision course with Earth. How would we know? And what could we actually do about it? Welcome to the Cosmos Quest. In this video, we're going to explore humanity's real plan to stop an asteroid, not science fiction. The actual strategies, technologies, and missions that NASA and space agencies worldwide are developing right now to protect our planet. The Chelyabinsk meteor was a wake-up call. But here's what keeps planetary defense experts awake at night. There are tens of thousands of near-Earth asteroids larger than 140 meters, big enough to cause regional devastation if they hit. And as of 2026, we've only discovered about half of them. That means there are thousands of city-killer asteroids out there right now orbiting the sun, and we don't know where they are. Some might be on trajectories that will eventually intersect with Earth. We just don't know yet. The good news? We have the technology to detect these threats. We have the capability to track them. And most importantly, we've proven we can actually deflect them. On September 26, 2022, NASA did something unprecedented. They intentionally crashed a spacecraft into an asteroid. And it worked. The mission was called DART, the Double Asteroid Redirection Test. It was humanity's first planetary defense technology demonstration, and it changed everything. The target was Dimorphos, a small asteroid moon just 160 meters across, orbiting a larger asteroid called Didymos. Neither posed any threat to Earth, but their characteristics made them perfect for this test. Launched in November 2021, the DART spacecraft was surprisingly small, basically a box 1 meter wide with 2 solar panels. It weighed just 570 kilograms, but it was fast, very fast. When it slammed into Dimorphos, it was traveling at 22,530 kilometers per hour, over 6 kilometers per second. The concept is beautifully simple. It's called the kinetic impactor technique. You hit the asteroid with a spacecraft at extremely high speed. The momentum transfer changes the asteroid's velocity just a tiny bit, but enough to alter its orbit over time. If you do this years or decades before the asteroid would hit Earth, that small change becomes a miss instead of a collision. Before DART's impact, Dimorphos orbited Didymos once every 11 hours and 55 minutes. Scientists predicted the collision would shorten that orbit by about 10 minutes, but the actual result exceeded all expectations. The orbit changed by 33 minutes. Why? Because when DART hit Dimorphos, it didn't just transfer its own momentum. The impact excavated tons of rock and debris that were blasted into space. This material acted like rocket exhaust, giving the asteroid an additional push. The recoil from this ejecta was responsible for most of the deflection. This was a game changer. It proved that with sufficient warning time, a relatively small spacecraft could prevent an asteroid impact. We can't stop hurricanes or earthquakes, but we can prevent asteroid collisions. But deflection is only half the equation. First, we need to find the asteroids, and that's where NASA's NEO Surveyor mission comes in. Currently, ground-based telescopes scan the night sky looking for moving objects that might be asteroids on near-Earth orbits. Since the Chelyabinsk event, detection capabilities have improved dramatically. As of early 2025, we've cataloged over 36,000 near-Earth objects, an enormous increase from just 10,000 in 2013. But ground telescopes have limitations. They can't look toward the sun. They're hindered by weather, daylight, and atmospheric distortion. Small, dark asteroids are incredibly difficult to spot until they're very close. That's why NASA is developing the NEO Surveyor spacecraft, scheduled to launch in the late 2020s. Operating from deep space, this infrared telescope will detect asteroids by their heat signature rather than reflected sunlight. It will be able to find objects coming from the direction of the sun. The goal is ambitious. Find 90% of all near-Earth asteroids larger than 140 meters within a decade of launch. These are the ones that pose the most severe impact risks to Earth, large enough to devastate entire regions. There's also an international effort underway. The International Asteroid Warning Network brings together observatories and space agencies from around the world to share data on potentially hazardous asteroids. The Space Missions Planning Advisory Group coordinates international response planning. If an asteroid were detected today with a chance of impacting Earth in 2032, follow-up observations would refine its orbit within months. Space agencies would launch a DART-style kinetic impactor within a few years to subtly change the asteroid's speed by just a few centimeters per second. Over time, that tiny nudge would compound, causing the asteroid to miss Earth by hundreds of thousands of kilometers. The kinetic impactor isn't our only option. Scientists are developing multiple deflection techniques, each suited for different scenarios. The gravity tractor method involves parking a spacecraft near an asteroid for months or years. The spacecraft's tiny gravitational pull slowly tugs the asteroid off course. It's extremely gentle and requires decades of lead time, but it's also extremely precise and doesn't require physically touching the asteroid. There's also the possibility of using nuclear devices, not to blow up the asteroid, but to vaporize surface material on one side. The expanding vapor acts like a rocket engine, pushing the asteroid away. This method could work on very short notice, perhaps just months before impact, though it's never been tested and raises obvious concerns about deploying nuclear weapons in space. For very large asteroids with years of warning, proposals exist for ion beam deflection, laser ablation, and even wrapping the asteroid in reflective material so solar radiation pressure gradually alters its course. The key insight from DART and ongoing research is that different asteroid types require different approaches. A solid iron asteroid responds differently than a loose rubble pile. A fast-rotating asteroid presents different challenges than a slowly tumbling one. That's why characterization missions, like ESA's Hera spacecraft currently on its way to study DART's impact site, are so crucial. We need to understand what these objects are made of before we know how best to deflect them. The universe is not empty. It's filled with debris. For billions of years, asteroids have struck our planet, reshaping continents, altering the climate, and driving species to extinction. But we're the first species in Earth's history capable of doing something about it. We're no longer at the mercy of random cosmic impacts. We have eyes looking outward, watching for threats. We have spacecraft that can reach any destination in the solar system and alter the course of celestial objects. The Chelyabinsk meteor injured 1,600 people and caused millions of dollars in damage. Yet it was tiny. A 140-meter asteroid could devastate an entire metropolitan area. A kilometer-wide asteroid could trigger global catastrophe. But with sufficient warning, we can prevent it. We can protect our planet. There are no known asteroids currently on collision course with Earth for at least the next century. But we're still searching and preparing. Recently, the interstellar comet 3I Atlas made headlines due to its unusual trajectory. Want to know why it caught so much attention? Watch the next video. And if you enjoy learning about space and the universe, please consider subscribing to our channel. Until next time, keep looking up and stay curious.